Hello, welcome to Forest Learn. In this video, we'll be comparing and contrasting stationary waves with progressive waves. Before we get into comparing and contrasting these waves, let me point out the following. It's common to hear standing wave instead of stationary wave. Okay, so I might use standing and stationary interchangeably throughout this video. Less common is traveling wave instead of progressive wave. It's something you might hear more at university level and beyond. Also in this video, to just save a bit of space, when I want to write nodes, I'll abbreviate this as a capital N, small s, and similarly, instead of antinodes, I'll write capital A and small s. So let's compare and contrast these waves. Really, there's just four things you need to be aware of: amplitude, frequency, phase difference, and energy when it comes to comparing and contrasting progressive and stationary waves. So let's look at each of these in turn. So here's a progressive wave, and if you look at, say, this green particle here, you can see that it oscillates up and down. And if you compare its amplitude, and remember amplitude means the maximum displacement of a particle or a point on the wave, okay, it's exactly the same as the maximum amplitude, or sorry, the amplitude of any other particle. So if I look at this green particle over here, it's got exactly the same amplitude as the first particle I was looking at. So any particle you look at on this progressive wave, its amplitude is the same as that of any other particle. Now the picture for stationary waves is quite different. Recall that there are special points known as nodes in a stationary wave. So for example, this green particle here is at a node. And nodes are characterized by being points of zero displacement throughout. So this green particle here, it's motionless, right? And if it's motionless, or theoretically it should be, that means its amplitude is zero. Now if we move a little bit to the left and look at this red particle here, you can see that it's oscillating, right? So its amplitude is non-zero. And as we continue to move to the left, the amplitude of the particles increases, okay, until we reach an antinode. So for example, this green particle here is near enough at an antinode, and you can see at this point here, the amplitude of this particle here is a maximum. Okay, so in other words, the amplitude varies in a stationary or standing wave depending on which point you're looking at. So let's record these observations in our table. Okay, so let's now talk about frequency. Let's go back to the progressive wave. Recall that frequency means the number of complete cycles or oscillations a particle or a point on the wave performs in 1 second. So we're looking at a progressive wave of 1.23 Hertz, meaning that this green particle here, for example, goes through 1.23 cycles every second. And in fact, that's true for any particle you care to look at on this wave. So the frequency is the same for all particles in a progressive wave. It's just that the particles may be oscillating out of step or out of phase with each other. Now if we look at a stationary wave, if we look at the nodes, again recall that they're points of zero displacement throughout, so there's no motion there. So since the particles are not moving at the nodes, that means that by definition those particles have zero frequency. Okay? All the other particles, however, so for example this green particle here and any of its red particles neighboring it, they again have exactly the same frequency, which in our example here is 1.23 Hertz. This is the frequency of the third harmonic that we're looking at here. Another way to think of this is that remember that frequency is related to the time period. Recall that frequency equals 1 over the time period. and the time period is the time that it takes for one complete cycle or oscillation to be completed. And if you look at these particles here in this loop between these two nodes, even though this red particle here has a different amplitude from the green particle at the antinode, the time it takes for either of these particles to perform one complete oscillation or cycle is the same. So if the time period is the same for the two particles, that means their frequencies must be the same. Okay? So any particle that is not at a node has the same frequency, the frequency of the harmonic. So let's record these observations again in our table. Now, the next thing we're going to look at is phase difference. Recall that the concept of phase difference quantifies how in or out of step 2 points on a wave are relative to each other. So if we go back to our progressive wave here, the phase difference between this green particle and this green particle here can be calculated very simply with this very straightforward formula once we know the wavelength of the wave and the separation or the distance between these 2 points. So with the wave paused, as a reminder, if 2 points are separated by half a wavelength, so for example this the particle at this trough here and the particle at this crest here, then recall that these 2 points are, or particles are, pi radians or 180 degrees out of phase. If we have 2 points that are separated by a quarter of a wavelength, then their phase difference is 90 degrees or pi over 2 radians, and so on. Now if we look at phase difference for a stationary wave, the situation is actually simpler. So let's focus for the moment on this central or middle loop here between these two green nodes. If you look carefully, all these particles in this loop are moving in step with each other. And remember, if particles are moving in step with each other, that means that they're in phase, or that the phase difference between them is zero. Another way of putting this is that when this green particle has maximum displacement, the same is true for its neighboring red particles in this loop here. They will also have maximum displacement. And similarly, when this green particle is on the equilibrium line or position, so it has zero displacement and is moving upwards, the same will be true for the red particles neighboring it. Okay, so really all these particles here in this loop here, in between these two green nodes, are just moving in step with one another. So let me just point out that this is actually a common misconception. So you can often get a multiple choice question where you're given a standing wave, you're told the wavelength, and you're given, say, the distance separating this particle here and another particle over here, and you're asked for the phase difference between those particles. And commonly what students will do incorrectly is they'll take that distance and the wavelength and use the formula for phase difference for a progressive wave, when in fact all that needs to be realized here is that because these particles are part of the same loop, okay, they're in step with each other, meaning that their phase difference is zero. So now that we've established that particles that are within the same loop are in phase with each other, so all of these particles in this third loop are in phase with one another, it's enough for us to just compare the phase difference between any particle in one loop, so for example this green particle here, and any other particle in another loop, so this green particle here. So let's have a look at the phase difference between this green particle and this green particle over here. So what you should notice here is that these particles appear to be moving completely out of step with each other. So when the displacement of this particle is, for example, a maximum positive displacement, the displacement of this particle will be a maximum negative displacement. And when this particle here is moving through the equilibrium position downwards, this particle will be moving through the equilibrium position upwards. So in other words, these two particles are pi radians, or 180 degrees, out of phase with each other. And the same can be said for any particle in this loop is pi out of phase with any other particle in this loop. Notice that the particles in this loop are separated by the particles in this loop by a single node. What if we were looking at a higher harmonic, for example this fifth harmonic, and we were interested in the phase difference between this green particle here and this green particle here? Let's press play and find out. Well, it looks as though these green particles over here and over here are pi out of phase as well. And notice that this particle is separated from this one by 1, 2, 3 nodes. So if particles are separated by an odd number of nodes, that means that they'll be pi out of phase. And this is assuming that we're not talking about the particles at the nodes, and so we're talking here about the particles that are actually moving in a loop. On the other hand, if particles are separated by an even number of nodes, such as this green particle here and this green particle here, then they will be in phase. Okay, so they'll have 0 phase difference. So an even number of nodes also includes particles not being separated by any nodes. Okay, so 0 is an even number. So this particle here and this particle here, they're not separated by any nodes, therefore they're in phase. So let's add all of these observations to our table. Just to be absolutely clear, because the particles at nodes are motionless, and as I said before, that means they have 0 frequency, it makes no sense to talk about the phase difference between nodes or between nodes and other points which are actually moving. So the last thing we need to discuss is energy, and the following will probably be mostly familiar to you. So recall that for progressive waves they transfer energy, whereas for stationary waves they don't transfer energy. It's as though the energy remains fixed. So for example, at the nodes are points of 0 energy and they remain points of 0 energy at all times, whereas antinodes are positions of maximum energy at all times. So there's no transfer of energy from one point to another point going on. In this video we've been comparing transverse, progressive and stationary waves on a string or a rope. But please be aware that everything we've discussed here and everything we've got written down in our table here holds equally well when it comes to a comparison between longitudinal, progressive and stationary waves as well. To end, I'd like to just point out that I'm very grateful for the simulation provided by FET that I've been using throughout this video, and I'll provide a link for this simulation in the video description area. So I'd strongly recommend you check that out and play around with the simulation yourself. It can be very useful in generating a good understanding of what's going on. And if you found this video useful, please like it, share it, and subscribe to the Forest Learn channel if you haven't already. And leave a comment if you have any questions or suggestions. So I'll see you next time. Thank you for listening.